All right, let's pull back the curtain on one of the most fundamental, well, forces in the entire universe. It's something you deal with every single day, but you almost never actually see it. We're talking about that invisible spark that powers pretty much everything: electric charge. You know exactly what I'm talking about, right? You're shuffling across a carpeted room, you reach for a metal doorknob, and zap! You get that tiny, surprising little shock on your fingertip. It happens to all of us. But have you ever stopped to think, what is actually going on there? Well, the secret behind that little zap, it isn't magic. It's pure physics. And the answer is hiding at a scale that is so incredibly small, it's honestly hard to even wrap your head around. So let's dive in. Okay, so the culprit behind that spark, the main character in our story today, is something called electric charge. And as we're about to find out, it's responsible for a whole lot more than just startling you when you go to open a door. So what is it really? Well, the textbook definition is that it's a fundamental property of matter, kind of like mass. It's just something that particles have. And this property creates a force that either pulls particles together or pushes them apart. But let's be real, that sounds a little dry. A better way to think about it is like this. Electric charge is the hidden engine of our entire world. It's the invisible power source behind basically every electrical and magnetic thing you can possibly think of. And to really get it, we need to know the rules of the game. And here's the good news. There are really only 3 main rules you need to know. These are like the unshakable laws that tell every single bit of charge in the universe how to behave. Let's break them down. Rule number 1 is just beautiful in its simplicity. There are only 2 types, or flavors, of charge. We call them positive and negative. And how they interact is simple. Opposites attract and likes repel. So a positive and a negative will always try to get closer, while 2 positives or 2 negatives will always push each other away. That's it. Okay, that seems easy enough. But that leads to another question, right? Can you have just any random amount of charge? Like, could you have half a charge? Or maybe a third of one? And the answer is a huge, resounding no. Which brings us to rule number 2. Charge is quantized. Now, that's a fancy word, but all it means is that charge only comes in tiny, individual packets. Don't get hung up on this number here. The important part is that 10 to the minus 19. That means it's an impossibly tiny piece. This is the charge of a single electron, the fundamental building block. You know, my favorite way to think about this is with Lego bricks. You can have 1 Lego brick. You can have 2. You can stack up 1,000,000 of them. But what you can never have is half a Lego brick. It's just not a thing. Electric charge works the exact same way. Every charge you'll ever see is just a bunch of these single fundamental units added together. And that brings us to our third and final rule. And this one is a really big one. Charge is conserved. This means you can't just make new charge out of thin air. And you can't destroy it either. The total amount of charge in the universe is fixed. All you can ever do is move it from one place to another. So if we can't create or destroy charge, then it has to be moving around. But how does it actually get from point A to point B? Well, this is where we get to what I like to call the Great Electron Shuffle. Turns out this shuffle happens in 3 main ways. First, you've got friction. This is literally just rubbing 2 things together. Think about a balloon on your hair. You're scraping electrons off your hair and onto the balloon. Then there's conduction, which is a transfer through direct contact, like a charged object is tapping another one. And finally, there's induction, which is kind of like magic. You can rearrange the charge in something without ever even touching it. And this brings us right back to where we started. That shock from the doorknob? As your feet rub against the carpet, friction scrapes extra electrons onto your body. Suddenly, you've got a negative charge. The second your finger touches that metal doorknob, a conductor, all that excess charge jumps from you to the knob. That's conduction. That little zap you feel is billions of electrons finishing their tiny electric journey. So, mystery of the doorknob solved. But why does any of this really matter on a grand scale? Because this isn't just about little static shocks. Electric charges, and this is no exaggeration, the force that shapes entire worlds. I mean, listen to how our source material puts it. It calls electric charge the source of all electric and electromagnetic interactions. Think about that for a second. Not some of them, not most of them, all of them. That's a huge statement for such a simple property of matter. What this means is we're not just talking about static cling on your clothes. We're talking about the force that actually creates light, the force behind every magnet. And maybe the most amazing thing of all, it's the force behind the chemical bonds that hold molecules together, the very chemistry that holds, well, you together. So the next time you feel that little zap, remember what it is. It's a tiny personal demonstration of a gigantic universal law. From that little spark at your fingertip all the way to the light traveling across galaxies from the most distant stars, it's all playing by the exact same rules. Which really leaves you with one final thought. What in our universe isn't shaped by this incredible invisible force?